This is the final installment of our videos on pool chemistry. We've already studied pH, total alkalinity, and calcium hardness. In this video, we're going to take a quick look at chlorine. Levels for chlorine should be between 1 and 4 parts per million. The ideal value depends on the type of chlorination and also your pool type. Like, for example, do you have a vinyl pool liner or a cement pool? As you know, chlorine functions as a sanitizer or a disinfectant, and it primarily works by oxidizing ammonia, like from sweat or the urea found in urine, and oxidizes organic matter. For example, microorganisms like bacteria, also leaves that might blow into the pool, and body oil and sunscreen. Chlorination is often accompanied by a stabilizer called CYA. Now, there's a number of sources that can be used to introduce chlorine into your pool. This is a bit confusing, but let's run through the list. There's chlorine gas, sodium hypochlorite or bleach, lithium hypochlorite, and calcium hypochlorite. Now, while there's so many to choose from, it should be noted that all of these methods ultimately produce hypochlorous acid, that's this, and hypochlorite ion, written either like this or like this. So it doesn't matter which one is used, the goal is still to produce hypochlorous acid and hypochlorite. Let's look at what happens if we introduce bleach into the pool. So the bleach dissociates into sodium ion and hypochlorite ion. The hypochlorite ion establishes an equilibrium. It functions as a conjugate base, and it pulls a hydrogen from water, creating hypochlorous acid and leaving a hydroxide. So notice that using bleach or using sodium hypochlorite as your method of chlorination actually causes your pH to increase because it adds base. So using sodium hypochlorite has introduced hypochlorite and hypochlorous acid. And once again, these are the two species responsible for oxidizing the organic matter in pools. So those are the two things we're interested in having in our pool. This is an interesting graph. Here on the right, we have hypochlorite, and on the left, we have hypochlorous acid. Now, before we go any further, it should be noted that hypochlorous acid, according to some reports, is 80 times more effective at oxidizing than hypochlorite. So this is concentration or percent, and this is concentration or percent. Now, this is pH. Look what happens at pH here, 7, 8, 9. Look what happens at pH 7.4. If we go up and over, you discover about half of the chlorine in the pool is hypochlorous acid, and the other half is hypochlorite. So about a 50-50 mix of each of these. If the pH goes up slightly, only to 8, you can see we've significantly decreased the amount of hypochlorous acid. And hypochlorous acid is once again our primary oxidizing agent. Imagine if you went up to like pH 9, you'd have just only a small percentage of hypochlorous acid. So here's an example where pH and chlorine are very dependent on one another. So it's important to keep your water balanced, to have all the parameters within range. We described free chlorine as hypochlorous acid and hypochlorite, the two things that we just looked at. These will combine with ammonia to produce combined chlorine. So we know that these things are responsible for doing the sanitizing. Here's an example of how that works using ammonia. So once again, the ammonia would come from like urea excreted in urine or sweat or something like that. Reacts with hypochlorous acid to make this compound called monochloramine. The monochloramine, which is here, can then react again with hypochlorous acid to make dichloramine. That dichloramine, right here, can then react with hypochlorous acid again to make nitrogen trichloride. Now, which one of these species predominates? That's heavily dependent upon concentrations of acid and concentrations of ammonia, and also on pH. So I don't know all the specifics about these, but I do know that these compounds have an odor, and these compounds are responsible for giving a pool its characteristic chlorine smell. So in fact, when chlorine levels are 1, 2, 3, 4 parts per million, like we said they should be, the chlorine should be essentially odorless, or the pool should be odorless. So what's giving the pool its chlorine smell are these things. This is an interesting little tidbit. Monochloramine, that's used in water treatment plants because it's stable. It's not affected too much by ultraviolet light, and it doesn't break down too quickly compared to like the free chlorines. So in other words, monochloramine will disinfect while in the distribution pipes. Does that make sense? So if municipal water has free chlorine introduced into it, by the time the water has reached your house and has sat in the pipes for an extended period of time, it's possible that there could be bacteria in there and that the free chlorine will be already broken down and not be able to oxidize the bacteria. But monochloramine being introduced intentionally, this will stay in the lines for a longer period of time. And now while its oxidizing strength isn't as great as the free chlorine, it still will oxidize and still will sanitize, but it just kind of lasts longer. So it's kind of neat because this isn't just pool chemistry, it's water chemistry, and it's used everywhere. Now, when those chloramines build up, we have to do something called superchlorination, or shocking, or breakpoint chlorination. That's the process of adding lots of chlorine until some of that combined chlorine or the chloramines break down. So let's look at this graph. Here we have parts per million, and here we have parts per million as well. This is chlorine being added. So let's look at this green line. This green line would be like adding free chlorine. So as we add free chlorine, you see the concentration doesn't change too much. That's because the chlorine that we're adding, that goes towards oxidizing or making chloramines. That's what this red line is. So these chloramines here, this is the stuff that smells in your pool. So as we do this thing called breakpoint chlorination, we add enough chlorine, in fact to about 10 parts per million in this graph, that all the chloramine gets essentially broken down and it gases off. And then when we add additional free chlorine, you can see that it climbs pretty rapidly because there's no ammonia compounds or no sweat for the free chlorine to react with. So this is somewhat of a confusing graph, and the chemistry is fairly involved, but the takeaway here is that there is combined chlorine in your pool. It should be less than this value. And to get rid of that combined chlorine, you superchlorinate to about 10 parts per million, and that's the breaking point where your chloramines gas off according to this reaction and produce like gaseous nitrogen and some other compounds. So I don't know how important this reaction is to know. I think it's the overall reaction, but the point is once again that hypochlorous acid will react with the ammonia compounds, and if present enough in a great amount, it will break them down to products that gas off and leave the pool. So the superchlorination should be done every week or two, depending on bather load. So free chlorine, as I mentioned before, decomposes pretty readily in the presence of ultraviolet light. Here's hypochlorite, and here's hypochlorous acid. Both of those, when exposed to ultraviolet light, will break down to these fairly, innocuous compounds in the water. So isocyanuric acid, or CYA, is used as a stabilizer. That keeps the chlorine from breaking down so rapidly. Now this is an interesting reaction. So here's the CYA, and here's hypochlorite. These two will react together and make this product here, which is dichloroisocyanuric acid. So there's a chlorine there and a chlorine there, and that came from hypochlorite. Now there's an equilibrium that's present, so there's some concentration of these and some concentration of these. And remember that hypochlorite does the oxidizing in our pool, along with hypochlorous acid. So this will be doing the oxidizing. When this oxidizes something, of course, it's gone. It's done the oxidizing. So this is removed. And Le Chatelier's principle tells us that if we take away this stuff, that this reaction will shift left and make more of it. So it's kind of like this is a bank or a reserve of chlorine in some ways. So not something major that we need to know, but certainly interesting. Now, if you're going to use stabilizer in your pool, which is a must if you have an outdoor pool where there's lots of ultraviolet light, then you want to keep the levels between 30 and 50 parts per million. So in review, pH, total alkalinity, calcium hardness, and chlorine. These are the 4 parameters that are essential for maintaining a properly balanced and sanitized pool. When you first get water that you're going to treat, we want to adjust the total alkalinity. Then we want to adjust the pH, then the calcium hardness, and lastly the chlorine. So it's important to do it in this order. When you're starting off with a pool for the first time, adjust total alkalinity, pH, calcium hardness, and then chlorine last. Here's the range for pH, the ideal value, and this can be achieved using these 2 products. Hydrochloric acid will decrease the pH, and sodium carbonate will increase the pH. Total alkalinity should be between 80 and 120 parts per million. Total alkalinity will increase when you add baking soda and will decrease when you add hydrochloric acid. Calcium hardness, here's the range. And you can increase the calcium hardness by adding calcium chloride. And remember, to decrease the calcium hardness, you pretty much have to do that through dilution. And lastly, the chlorine. Chlorine can be added by introducing sodium hypochlorite or bleach. So thanks for watching this series on pool chemistry. I hope that by understanding the chemistry that it makes maintaining your pool a little more meaningful. Thank you.